In this review tape, we're going to be going over our work on logarithms. Let's start by recalling the basic definition of a logarithm. If we have a positive number b, which is not 1, when we say y is the log of x to the base b, this is equivalent to saying x is equal to b to the y power. That is, the log of a number x to the base b. If y is the log of a number x to the base b, y is the power that you have to raise the base to get the number x. Okay, in the first problem, I would like you to translate the following from log form to exponential form. Okay, we'll have in part A, the log of 16 to the base 2 is 4. Part B, the log of 1/9 to the base 3 is minus 2. And in part C, the log of 4 to the base 8 is 2/3. Okay, now what I want you to do is write an equivalent expression involving exponents in place of each of these logarithmic equations. Okay, using this basic way of transferring the idea of a logarithm. The log of 16 to the base 2 is 4. Okay, because 4 is the power that you would have to raise the base to get 16. The log of 16 to the base 2 is 4. The log is 4, because 4 is the power that you'd raise the base to get the number. Okay. Similarly, an equivalent expression in exponents over here would be that the log of 1/9 to the base 3 is minus 2, because minus 2 is the power that you would have to raise the base 3 to get 1/9. 3 to the minus 2 is 1 over 3 to the 2. 1 over 3 squared, of course, is 1/9. And finally over here, the log of 4 to the base 8 is 2/3, because 2/3 is the power that you would have to raise the base 8 to get 4. This last one might need a little explanation. Let's look at 8 to the 2/3. I just want to show you that 8 to the 2/3 is really equal to 4. 8 to the 2/3 power could be thought of as 8 to the 1/3 power squared. And this could be thought of as the cubed root of 8 squared. The cubed root of 8, of course, is 2. 2 squared, or 4. So 8 to the 2/3 power does come out to be equal to 4. Okay, now I would like to go the other way. I'm going to give you expressions in exponents, and you are to write equivalent expressions involving logarithms. So translate from exponential form to log form. In A, 5 squared equals 25. In B, 2 to the minus 3 power is 1/8. And in C, 9 to the minus 3/2 power is 1/27. And if it helps, I can write down the basic relationship again. B to the y equals x is equivalent to y equals the log of x to the base b. Okay, y is the power that you'd have to raise b to get x. All right. Over here, an equivalent expression following this would be that 2 is the log of 25 to the base 5. 2 is the log. It's the power that you would have to raise the base 5 to get 25. Over here, we could write down that minus 3 is the log of 1/8 to the base 2. Minus 3 is the log here. Minus 3 is the power that you'd have to raise the base 2 to get 1/8. 2 to the minus 3, of course, is 1/8. And finally, over here, I'm assuming that you accept this as true. 9 to the minus 3/2 is 1/27. Just take a quick look at that. 9 to the minus 3/2 is 1 over 9 to the 3/2. 1 over 9 to the 1/2 cubed. Okay, 9 to the 1/2 is the square root of 9. The square root of 9 is 3. So we get 3 cubed. 1 over 3 cubed is 1 over 27. So 9 to the minus 3/2 is 1/27. And over here, we could write it this way, or we could say the log of 1/27 to the base 9 is minus 3/2. Okay, minus 3/2 is the power that you'd have to raise 9 to get 1/27. All right, in the third problem, we want to solve for x in each of the following. Okay, in part A, the log of 32 to the base 2 is x. Okay, don't let this upset you. X doesn't have to be over here, or it doesn't have to be the log of x. It can be any of the unknowns. You just have to understand what's going on here. If I say the log of 32 to the base 2 is x, that means, this is equivalent. If the log is x, that means x is the power that you'd have to raise the base to get the number. You should be able to, even if you see the unknown someplace else, you should be able to reason this out. The log is the power that you'd raise the base to get the number. Okay, now we'd like to solve this equation for x. If you happen to know that 2 to the 5th power is 32, then you know automatically that x is equal to 5. If not, what we try to do is get like bases on the two sides. Okay, this is 2 to the x. We can then say 32 is 2 to some power, figure it out that it's 2 to the 5th power. And then when the answers are the same and the bases are the same, the exponents have to be the same. So we get that x equals 5. In part B, the log of 1/16 to the base 4 is x. Okay, this is equivalent to saying, okay, the log is x, so x must be the power that you'd have to raise the base to get 1/16. Okay, now, to figure this out, we would try to get, since we have a 4 here as a base, we'd like to write 1/16 in terms of a power of 4. And we realize, of course, that 16 is 4 squared. So we have, okay, for 1 over 16, 1 over 4 squared. And then we can say, well, 1 over 4 squared, that's 4 to the minus 2 power. So now we have it. We have two expressions. They're equal. The bases are the same, so the exponents must be the same. X equals minus 2. Okay, in part C, log of 16 to the base 8 is x. Okay, so x is the power that you would have to raise the base 8 to get 16. Okay, now in the other examples that we worked out, okay, let's look over here. We were able to get the right-hand side in terms of the base on the left. We had a 4 here, and we were able to write this as a power of 4. We had a 2 over here. We were able to write 32 as a power of 2. Okay, now if we're going to restrict ourselves to integer powers, we're not going to be able to handle it in the same way here. So if we're trying to, in other words, write an integer solution. Now what we can do, however, is say, look, they're both powers of 2 here. We could say 8 is really 2 cubed. And 16 is really 2 to the 4th. And then we say that 2 to the 3x is 2 to the 4th power. And now we do have it in the situation where we have the same bases, and we simply can equate the exponents. 3x equals 4, x equals 4/3. 8 to the 4/3 power is 16. And this one is not obvious. It's not something that you would just do in your head like some of the other ones here. You'd actually have to work it out. Okay, in part D, we have the following. The log of 1/9 to the base 27 is x. This is equivalent to 27 to the x power is 1/9. X is the power that you'd have to raise 27 to get 1/9. Okay, and let's try the same kind of procedure we used on the last example. We'll recognize that 9 is 3 squared. So this is really 1 over 3 squared. And here 27 is 3 cubed. So this is 3 cubed to the x power. This is 1 over 3 squared, or 3 to the minus 2 power. 27 is 3 cubed. 27 to the x is 3 cubed to the x power. 9 is 3 squared. 1 over 3 squared becomes 3 to the minus 2. So we have that 3 to the 3x power is 3 to the minus 2 power, from which we can equate the exponents. 3x equals minus 2, x equals minus 2/3. Part E, I'm going to change it around. And all the other ones, the unknown was on the right-hand side. Now I'm going to make the unknown the base. The log of 4 to the base x is 1/3. Okay, we follow the similar procedure. We say, well, if the log of 4 to the base x is 1/3, then 1/3 must be the power that you'd have to raise x to get 4. Okay, now we'd like to solve for x. If you have x to the 1/3 here, this is like the cube root of x equals 4. You'd have to cube both sides to get x alone. Okay, so let's raise both sides to the 3rd power. And you get that x is equal to 64. The cube root of 64 is 4. Okay, so to isolate x here, we cube both sides. We don't take cube roots. We cube both sides. We get x equals 64. All right, in the next example, number 4, I want to use properties of logs to simplify the following expressions. And in part A, we have the log to the base b of the square root of x times y squared over z. Okay, let's just go over the basic properties of logs. To begin with, the log of a fraction is the log of the numerator minus the log of the denominator. The log of a product is equal to the sum of the logs of the factors. And finally, the log of something to a power is the power times the log of the something. Okay, so let's use those properties one at a time and see what we get here. Okay, we'll start by saying, well, this is a fraction. It's the log of the numerator, the square root of xy squared, minus the log of the denominator, and both of these are to the base b. The log of the top minus the log of the bottom. Okay, now we can say, well, the square root of x is really x to the 1/2 power. This is the log of x to the 1/2 y squared b minus the log of z to the base b. This was not a property of logs. I'm just rewriting the square root of x as x to the 1/2 power. The only property I used so far was that the log of a fraction is the log of the numerator minus the log of the denominator. Now over here I notice a product. The log of a product is the sum of the logs of the factors. So I can say it's the log of x to the 1/2 plus the log of y squared, both to the base b, minus the log of z to the base b. And then finally, I can use a property that says the log of something to a power is the power times the log of the something. That is, you can bring the power down in front as a coefficient. So I can make this 1/2 the log of x to the base b plus 2 times, bringing the power down, the log of y to the base b minus the log of z to the base b. Okay, and there we have it written out. Okay, so once again, remember the log of a fraction is the log of the numerator minus the log of the denominator. The log of a product is the sum of the logs of the factors. And the log of something to a power is the power times the log of the something. Okay, I just want to point out something to you. If you have, for example, the log of x plus y, this cannot be written as the log of x plus the log of y. Okay, the log of x times y, the log of a product, is the sum of the logs of the factors. But if you have the log of x plus y, you just leave it like that. The log of a product, that is the sum of the logs of the factors. Now let's do part B. The log to the base b of the cube root of x over y z cubed. The same type of problem. I want to use properties of logs to simplify this. Now, we'll start off the same way. It's the log of the numerator minus the log of the denominator. The log of, now instead of the cube root of x, let me write that as x to the 1/3 power. That's just rewriting it with exponents. That's not a property of logs, okay? Minus, now, the log of a product is the sum of the logs of the factors. You have here a product. But because of the minus sign here, okay, let's make parentheses or brackets and write it as log of y plus the log of z cubed, both to the base b. All right. Now, finally, we can say the log of something to a power is the power times the log of something, giving us 1/3 the log of x to the base b. minus, now you can distribute this minus sign through the parentheses, log of y to the base b minus the log of z cubed becomes minus 3 log of z to the base b. Okay, now I just want to point something out between these two problems. Over here, they both were logs of fractions. Okay, over here, the product occurred in the numerator, so it was the log of a product was the sum of the logs of the factors, and there was no difficulty with parentheses or anything like that. Here, however, the product occurred in the denominator. So when you say the log of the numerator minus the log of the denominator, you have this minus here, like a minus 1. Now, when you say the log of a product is the sum of the logs of the factors, here you must put brackets or parentheses and then distribute this minus sign through the brackets. Okay? It is very essential over here, otherwise you'll have the wrong answer. All right. Now let's go to problem 5. Problem 5 involves scientific notation. It's a preliminary to using the log tables. If you look in the log tables, okay, you'll see that they're given for they give you the logs of numbers between 1 and 10. And if you want to deal with a number, say, outside of that range, we have to first write the number in scientific notation. That is, we want to write it as a number between 1 and 10 times a power of 10. So let's try some. Write in scientific notation. $48,300 and also 0.0483. Okay, now what I'm interested in doing here is writing it as a number between 1 and 10 times the power of 10. And in both cases, the number between 1 and 10 is going to be the same. This is going to be 4.83 times 10 to some power. And also, this will be 4.83 times 10 to some power. Remember that if you multiply, when you multiply, say, by 10 to the power p, let's say p is a positive integer. When you multiply by 10 to the p power, that has the effect of moving the decimal p places to the right. On the other hand, if you multiply by 10 to the minus p power, once again, p is a positive integer, so this is 10 to a negative number. This has the effect of moving the decimal p places to the left. Okay, remembering that, we should be able to figure this out. 4.83 would be like so. What do we really want? 48,300. So the decimal place would have to move once, twice, 3, 4 times to the right. So this is going to be multiplying by 10 to the 4th power. You say to yourself, what is 4.83? Where is it over here? It's over here, and you wanted 48,300. So you'd have to move the decimal 1, 2, 3, 4 places to the right. So you multiply by 10 to the plus 4 power. Down over here, 4.83 times 10 to what power to get 0.0483? Well, 4.83 would look like so. And we would like, really, to have 0.0483. So we'd have to move the decimal once, twice to the left. If you move the decimal to the left, that makes it a negative, and twice, so 10 to the minus 2 power. 4.83 times 10 to the minus 2, the decimal goes 2 places to the left, giving you 0.0483. Here the decimal goes 1, 2, 3, 4 places to the right, giving you 48,300. Okay, now, keeping that in mind, in problem number 6, I would like us now to find the log of 48,300 to the base 10 in part A, and also in part B, find the log to the base 10 of 0.0483. Okay, and as I said, the first step, if you try to look up 48,300 in the book table of logs, say in the back of your book, you would see that logs are not given in terms of such large numbers, only for numbers between 1 and 10. So the first step is to say this is the log of, now 48,300 can be written as 4.83 times 10 to the 4th power. We just did that in the preceding example. All right. Now 4.83 is a number that you can find in the back of your book. But first, let's use properties of logs. We say the log of a product is the sum of the logs of the factors, so it's going to be the log of 4.83 to the base 10 plus the log of 10 to the 4th to the base 10. Now, if you go to the back of your book in your table of logs, you will look up 4.83, and you will see the log of 4.83 to the base 10 is 0.6839. So over here, the log of 4.83 to the base 10 will write 0.6839. And over here, we have to figure out what to write. Okay? We need the log of 10 to the 4th to the base 10. Okay? Let's say this is x. We're not sure what this is. Remembering how the log definition works, this is the log of some number to the base 10 is x. That means that x is the power that you would have to raise the base to get the number. The log of this number to the base 10 is, if x is the power that you'd have to raise 10 to get the number, but 10 to the x is equal to 10 to the 4th, then x must be 4. And actually, these problems are done usually in your head. You'd simply say the log of 10 to the 4th to the base 10 is just the exponent 4. The logic being that 4 is the power that you'd have to raise 10 to get 10 to the 4th. So we get, as our final answer, 4.6839 for the log of 48,300. Now let's go back over here and look in part B, the log of 0.0483. First step, of course, is to write this in scientific notation so that we can use our log tables. Well, in the preceding example, in 5b, we saw that 0.0483 could be written as 4.83 times 10 to the minus 2. So let's do that. Let's write it as 4.83 times 10 to the minus 2. Okay? Then we say, remember this came from the preceding example, it's 4.83 times 10 to the minus 2. The log of a product is the sum of the logs of the factors. So we have the log of 4.83 to the base 10 plus the log of 10 to the minus 2 to the base 10. Now, 4.83, we know from our table, is the log of that is 0.6839. The log of 10 to the minus 2 to the base 10 would simply be minus 2. Minus 2 is the power that you'd have to raise 10 to get 10 to the minus 2 power. Okay, so you can write 0.6839 minus 2. If you're ever using a calculator to find the value, they will probably the calculator would give you the answer as actually minus 2 plus 0.6839. It would come out to be minus 1.3161. Okay, but if you're not using a calculator, if you're using tables, we generally leave it in this form, or we write it equivalently as 8.6839 minus 10. Okay, 8 minus 10 is the same minus 2, and sometimes it's more convenient to have it in this form. Okay, but I just want to point out that if you're using a calculator, the calculator would actually perform the subtraction and give you the algebraic answer as a minus 1 point something. Okay, and in the last problem on this tape, I would like to find the antilogs of two numbers, working the opposite way Okay? I'm going to give you the log of a number. You have to go back and figure out what number it was. Okay? Here we are finding the logs of numbers. Okay? Now I'm going to give you a problem where we start with the answer and you figure out this was the log of what number. So given, I'll give you the table value. Given that the log of 5.98 to the base 10 is 0.7767, I want you to find A, the antilog of 3.7767. Okay, and in B we'll have another one. Okay, so we can let n be the number whose log is 3.7767. That is, say that the log of some number is 3.7767, and we want to figure out what is n. This is what we mean by the antilog. The log is 3.7767. What must n have been? And we're going to sort of undo the steps that we did in problem 6. Okay, maybe it would help to just go over for a second here. You see the final answer, 4.6839. Going back, the first thing to do would be to break it up, put the 4 separately, the 0.6839. The 6839, okay, with the decimal point, this is the number that you would find in your log tables. You can go back and figure out it was a log of something. This will lead eventually to a power of 10. Okay, so let's do that. The log of n, and if you don't see anything specified, we're talking to the base 10 here. The log of n is going to be 0.7767 plus 3. Or you can say 0.7767, well, that's the log of 5.98 to the base 10. Okay, I'm telling you, giving you this table entry, you would now look in the table, find 0.7767, and see which number had a log corresponding to that, and it turns out it's 5.98. And then 3, you would say, well, that is the log of 10 cubed to the base 10. The logic, again, being that the log of 10 cubed to the base 10 is 3, since 3 is the power that you'd have to raise 10 to get 10 cubed. Okay, so the log of n is the log of this plus the log of that. Well, if the log of a product is the sum of the logs of the factors, we can work backwards and say the sum of the logs of the factors here is the log of this product, 5.98 times 10 cubed. The log of a product is the sum of the logs of the factors. Okay, if the log of n to the base 10 is equal to the log of this number to the base 10, then n must be equal to this number. N must be 5.98 times 10 cubed, or multiplying by 10 to the third power has the effect of moving the decimal 3 places to the right. 1, 2, 3. So we have 5,980. The idea is to get it down to the point where you have the log of n is the log of some number, so n must be that number, and then you multiply by 10 cubed has the effect of moving the decimal 3 places to the right. Okay, and I would like to finish off with another anti-log example. Okay, in part B, I want the antilog of 6.7767 minus 10. Okay, so we'll say the log of n, base 10, is this. And we can start by saying 6.7767 minus 10 is really 0.7767 minus 4. Okay, 0.7767 plus 6 minus 10 to the minus 4. And then we can say, well, the log of n is this minus this. Now, 0.7767 we know already is a log of 5.98. To the base 10. And minus 4 could be thought of as the log of 10 to the minus 4 power to the base 10. Minus 4 is the power that you have to raise 10 to get 10 to the minus 4 power. Now, using properties of logs, the log of a product is the sum of the logs of the factors. Using that in reverse, we get 5.98 times 10 to the minus 4. The log of that must be equal to the log of n. The log of a product is the sum of the logs of the factors. And now we're down to the point we say the log of n is equal to the log of this, therefore n must be equal to this, 5.98 times 10 to the minus 4. And when you multiply by 10 to the minus 4 power, you move the decimal 4 places to the left. Once, twice, 3, 4. So we're going to get 0.000598.